we get also protection out of this. You can't see outside of your process space. Okay, because of that, you can't mess with someone else. They can't mess with you. Okay, so we've got this isolation, and that's going to, as soon as we can isolate it, we can protect it. And you know what we can do with protection? We can have security. Okay? If we don't have isolation, we can't have protection, and we can't have security. So this isolation is setting us up for a bunch of more advanced ideas. Okay? So let's talk about memory. We're going to talk about it through the memory API. Okay? Has anyone ever heard the term automatic variables? Okay. It's not a term that's used much anymore. It used to be heavily used by people who wrote impossible to understand textbooks. All we mean by automatic variables is that the space for them, the system goes and manages it for you. And the classic example of that is our stack. How many of you have ever written a line of code that said allocate more memory for my stack? For your stack? You can't. It's managed automatically for you. How many of you have remember from CS201 that when we want to actually allocate something in a stack frame, remember stack frames? Okay, the first thing that the code that gets inserted is we subtract from the stack pointer and then we store the data. But we didn't write that code. That was done for us by the compiler. Right? So the stack gets managed automatically. That's why we call them automatic variables. Okay? I just like to call them local variables. And then remember that all local variables are stored in a stack frame. The nice thing about that is that stack frames, when we're done with a function, what happens to a stack frame? It goes away. Okay? There's a couple different ways that can occur, but for the most part, we just say the stack is now someplace higher up in memory. We don't delete all that data. Okay? And that's fine. Yes?
So when you call malloc, is that on the heap then,
Malloc
not the stack?
allocates dynamic memory, and that's always on the heap. And there's another one called alloc-A, but alloc-A allocates on the stack. So you can allocate on the stack,
Okay.
just not done a lot.
Gotcha.
Okay. Now, yes.
So if you have a function that has like local variables that are allocated on the stack, and the variables are out of scope, then the variables are just moved in memory, and is that why you can't access them anymore?
No, you can still access them. So if I go to the end of my, so he's talking about variables going out of scope. So let's in my function, I declare x. And in my return value, I return the address of x. Okay. Now, when that function ends, its stack frame is popped, we call it. All right. And we believe, we convince our brain that it's actually deleted, but it's not. You can still access that address in memory, but you have no guarantee what its contents are, because the next time you go and make another function call or something like that, you'll create a new stack frame, won't you? And you will overwrite that address with new stuff. You can get some really interesting behavior. It's very, very non-deterministic. Okay, incredibly difficult to debug. All right. So if I see something at the end of a function that says return address of, at that point I just stop. I go, something is badly broken here. Should never return an address. Now maybe what I did was I malloc some space, right? That's on the heap. But I had to give it a local variable name. So I can't return the address of x. It's going to get written over eventually. Right? You have to be careful about this. If your memory needs to be accessible above your stack frame, that is, after your function returns, we have to use pass by reference, don't we? We have to pass in a variable for them to stick the information in, because that variable is in a higher stack frame. So it's still good. I can access higher stack frames than mine because they can't be removed from the stack until my function ends, can it? Okay. So there's some cool stuff that's happening there. The heap. Okay. The heap is cool. Oh, by the way, if your stack at any particular point in time is only using so much memory, and if it needs more memory, the operating system will grow it for you. It's not so on the heap. Preface this by saying that our textbook takes a classic approach to talking about the heap, and it's kind of an old way of looking at it. It's not the way most heaps are managed these days, but it's very, 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 very close. Okay. So if we do something like, X is a pointer to some memory. Okay. Couple things about this. X is a local variable, isn't it? Have I told you guys how I read these? Okay. I read those declarations right to left. So X star means pointer. X is a pointer to an integer. Okay. Or excuse me, X is an integer pointer. And we go out here and we go ahead and allocate the size of an int. X is going to take how much room? Int? When you say int? When you say not int? Okay, someone tell me why they said not int.
Because
It's actually the size of the architecture word, isn't it? So if it's a 64-bit system, a pointer is a 64-bit system. It's a 32-bit system, it's a 32-bit pointer. Okay. Historically, we had 32-bit systems for most of the time that I've been alive. Okay. As a result, we often say that a pointer is an int, because 32 bits is a C int, and it's also the size of a pointer on a 32-bit system. We've got to start changing our terminology. Okay. And the way I try to encourage my CS201 students is to say that a pointer is the size of an architecture word, or the size of the architecture. Okay. So in XV6, yes, a pointer is the same size as an int, but please do not call it an int. You're going to be programming primarily on 64-bit systems. And you may, for all I know, start calling them longs. But the reality is there's 64 bits or 8 bytes in a 64-bit system, not an int. So this is a pointer to an int. A pointer itself always occupies the size, a memory region the size of the architecture. So if we're in a 32-bit architecture, it's going to be 4 bytes. If we're on a 64-bit architecture, it's going to be 8 bytes. If we're on a 16-bit architecture, it's going to be 2 bytes. Okay? But it's the size of the architecture. So when your program is running, all pointers are the same size. They can point to regions of memory that are accessed by different sizes. So here we say it's an integer. So when we go and read something through X, we're going to read 4 bytes at a time. If it was a char pointer, we'll read it a byte at a time, won't we? Okay, unless we do some weird casting things. Now, malloc is
I was wondering why was the stack and the heap chosen as the data structures to manage data in C? Or I guess why was the stack?
It's actually, yeah, so they map cleanly down to the concept that, memory is an array. Okay, so they map fairly cleanly because they're contiguous data structures, particularly the stack. And they're very, very simple to manage. And in the early days, it was all about speed. It was all about getting that to work as fast as we could. So it's very close to the hardware conceptually, and then it's very easy for us to implement, so it has low latency.
Would there be any data structure that would be better to use than the stack?
Oh, so replacing the stack with a different data structure? There's a lot of discussion that goes on around that. The fact of the matter is we get hardware support for things like push and pop. And because they're an array, it makes it simple for us to implement push and pop in hardware. The actual heap and how that's actually managed behind the scenes, the heap looks to us like a contiguous block of memory. It's not, and oftentimes is implemented under the covers with a hash table. Maybe a hash table in each bin has like a red-black tree or something like that in it. But it still looks to our programs like it's just a contiguous chunk of memory. Now, how many of you used malloc in C++? Okay, directly. Called malloc in C++. You don't, do you? Okay. So it turns out we're abstracting you further away from the memory. You see it as an object in C++. You don't see it as a region of memory. You see it as an object, and the object has entry points, method calls, and it has private data and things like that. So as we go up into functional and OO languages, we're starting to be even further away from the concept of what malloc is doing for us. And also how heaps and stacks work. Does that help?
Okay.
And your new, I believe, in all OO languages, when you do a new, that's heap memory, because it gets malloc under the covers. So I'm 99.9% sure that that's all coming out of the heap, not the stack. So malloc is kind of interesting. And a lot of books will give you this line of code, which is not how we want you to do it anymore. We want you to make the call this way. Okay? It turns out that modern compilers, modern systems, all that kind of stuff, we know that because your sign on the left-hand side is a double, we know that there's a bare minimum an implicit cast. And malloc returns a void, which can be cast to anything. So this we used to put in, even though we also didn't need to do it, we put it in to basically tell other programmers that we knew what we were doing. Okay. Now we take it out, so we're telling other programs that we know what we're doing. Okay. This is old style. Right. And once again, you graduate from here, you go off into industry. They may, wherever you wind up working, they may be fanatical about which version you use. And that's usually so they have a consistent programming style. So figure out what the programming style is for where you're at. How many of you have ever malloc size for a string? Go, I want to put a string in here, and I need to dynamic allocate it, so I'll malloc space for a string. Okay? It's kind of interesting when you malloc space for a string. Okay? The idiom, what we want you to do, is do malloc the length of the string plus 1. Why?
So that you have something at the end to tell it this is the end of the string.
Yeah, so it turns out that when we call string length, this is one of my pet peeves about string length, it only tells you the number of characters, quote, in the string, okay, which means it doesn't count the null terminator. Has anyone ever been burned by that?
Oh, yeah.
Copy some stuff over, and then all of a sudden your string was 7,000 characters because the null terminator went away? Wasn't that fun? Okay, and C knows it does this. They know that it does this. That's why in the XP6 kernels we have save string copy. Save string copy will automatically terminate your string no matter what, even if it has to overwrite some part of your string. By the way, string copy, strncpy, doesn't null terminate either. Okay. The interesting thing here is that this idiom is making use of the following idea, which is wrong. If we copy into this new area, this is called destination, and we copy string length, we like to say that it actually copied the null terminator, but it doesn't. It only copies string length of bytes. But many people rely on the fact that most implementations for malloc will zero the memory when it returns to you, which means that it's already put a null character there. Has anyone ever programmed on Windows and done a malloc? Okay, I was just reading this morning on Stack Overflow that Microsoft still, in their malloc, returns where the memory is all initialized to CD. CD, all the way through it. There is no null terminator in that location, ladies and gentlemen. Okay. It's just not there. In fact, if you go off and read the C standard, you'll find out that malloc's job is to return a pointer to uninitialized memory.
Isn't that like alloc is meant to be kind of cool?
Yeah, so calloc is going to fix this problem. And I'm going to send out a link, or I'll put in this document, a link to the very, very good discussion on Stack Overflow about the issues. Because if you need this thing to be null, because you're relying on that last space to be null, then you might have to use something like memset to set it all to null. Okay. So if you're relying on even one byte out there being a particular value, and you've used malloc, you have to set it to that value. All right. So let's say we allocated, instead of string length, let's say we put 1024. We say that, the maximum string size on Linux, or let's see, actually the maximum argument size I think is 1023 characters. Okay, so I'll allocate 1024 and I'll automatically have that terminated by a null. Well, no, because you use malloc. Oh, that's okay. I'll just take the last address and store a 0 there. Yay, good for you. It's a null string, but guess what? If your string is less than 1024 characters, between the end of that string and the null you just put in is random garbage. The only saving grace for you is it will copy your null pointer, because you're going to tell it to copy 1024 bytes. So it's going to copy that string plus the null pointer plus all the rest of it. But if you copy just string length of the string into that buffer, and it's less than the allocated size of the buffer, you have garbage out there. Fortunately, in most systems, we get a null page. Okay? But not all. It is an amazing source of bugs. Just ridiculous amount of bugs. Okay. And we know about free. What's the equivalent to free in OO?
Delete.
Delete. Okay. How many of you just allocate a bunch of objects and then just terminate the program and don't bother to delete? It works. Okay. What would Carla do? She'd come along and frown, at the very least you frown. Now, it works fine in short-running programs. Right? But how you practice on your small programs is how you will write your big programs. So if you knew, you must always delete. If you malloc, you must always free. Can you get away with not doing it? Sure. Does it make you a good programmer? No. What does it make you? Lucky. It makes you lucky. Okay? It's a type of memory leak. We want to avoid memory leaks. Okay? So here's that trick here we talked about before. You know, has anyone ever done this where they declared a pointer for the string they want to copy and then forgot to put memory behind it? Okay. Did you know that sometimes it'll work and sometimes it won't? It depends on what's out there. Okay. Now, it's entirely possible that when we initialize this, that desc got set with zeros. Or it could be a random number.
So unless you explicitly set that to null, then it doesn't automatically set it to null? If you just declare a pointer of some type?
It depends upon your system. I have to go back and look. I don't think the C standard currently requires that to be zero initialized. It might.
Yeah.
I think
Is it the
even-
standard?
No, it
Oh,
can
it's
be
still,
whatever.
it's still implementation specific now. Okay, so it's not defined. Once it's not defined, it means, well, we can all get together and make it convenient, or not. Okay? And there'll always be somebody out there that goes, or not. So, and because it's going to take time to set that to zero. Okay? And, you know, sometimes people are pretty fanatical about speed to the point where they don't care if that messes up your programming. Because programs do something very, very interesting. And that is, programs do what you say, not what you mean.